So let's run through some of the answers here. So, for instance, 9 to the second power would be 81. Not a big surprise there. If we move on down, we've got 64 is the third power of 4. So 4 to the third power is 64. Then how about 81? 3 to the fourth power is 81. So we get a 4 here. But here's where they start to get a little bit interesting and challenging. Maybe not so much with this first one. What power of 7 gives you 7? That'd be the first power. Good. How about 8? What power of 8 gives you 1 over 8? You guys got that one? Yeah, -1. And I think the trick in working with this one is to recognize that this number down here is really 6 squared. So what power of 6 is going to give you 1 over 6 squared? What's going to put that in the denominator? Victoria? -2. Good. So 6 to the -2 is really 1 over 6 squared, or 1 over 36. And a couple of you are struggling with this one. I can have sympathy for that. What power of 7 gives you the square root of 7? Dylan?
1/2.
Yeah, 1/2. So something to the 1/2 power and the square root are the same. In fact, for me, that's a shortcut on the calculator. When I want a square root, I don't always hit the square root key. I usually do that for demonstration purposes. But if I needed the square root of a number, I also do 6, like 36 raised to the 0.5. Well, that's to the 1/2 power. That's essentially the square root. So kind of a nice little shortcut there for you on the calculator if you need it. Log base 10 of 10, well, that's not too bad. That's just a 1. And then a 2 and a 3 and a 4, etc. Do you see a little pattern here with the log and the number of zeros? Like 2 zeros, log base 10 of 100 is 2. 3 zeros, log base 10 of 1,000 is 3, etc. But you might struggle a little bit more with these last couple. And if you do, there's good news. The logarithm base 10 is built in directly into your calculator. So if you wanted to, you could just calculate that right off your calculator. You don't have to think too much. log, log of 0.01, should be -2. And log of 0.001 would be -3. Okay, so those are our last two on that column. And the whole idea is to just get used to logarithms. Logarithms are intimately tied to exponents. It's what power of the base gives you this number. And being able to write it, go back and forth, is something that's going to help you out immensely. So speaking of going back and forth, let's go the other direction. We'll start out with exponential expressions and rewrite them with logs. Now, if you've got this written at the top of your test paper or final exam, whatever, you can always refer back to it and rewrite things like this. A to the y equals x is the same thing as log base x, or excuse me, base a of x equals y. So all we have to do is kind of label these things and rewrite them. So the base is 10, so it's going to be log base 10 of this number, so that's of 1,000, that's my x, equals the exponent, which is 3. So log base 10 of x, so excuse me, log base 10 of 1,000 equals 3. Now that kind of work gets a little bit more challenging as you move down the list of problems, but it's more or less the same. What base logarithm am I going to take down here? Log base 3 of 1 over 81 equals -4. How about the next one? Brandon, maybe you can help me out. What base logarithm should I take here? Log base m of perfect. Log base m of p equals n. And we'll do a couple more here. So, Olivia, how about the next one? Log base b of 2/3 equals r. Perfect. And I'll do the last one here. log base 4 of 8 equals 3/2. Now, if you're worried that, like, you know, if I had to calculate this way, what power of 4 gives me 8, I'd never come up with this. Don't worry. The nice thing about the calculators that I lent you, or a lot of the calculators that you have, is that they now have this operation built in. This wasn't the case when I first started teaching this course. So people had to work a little bit harder. They had to use what's called the change of base formula. I'll throw that up on the board in just a second here. But if I want to calculate log base 4 of 8, I can do that from my calculator. So there's a couple places to access it. The one that I'm most comfortable with is off the math menu. And you got to go to the right one to get to number. Or see, did I lie? Or is it here? Let me go up. Oh yeah. Now, it's actually off the first column. You got to go up, log base something. And now you can just type in the somethings, like for instance, log base 4 of 8. Now it's going to give me 1.5, but I can then turn that into a fraction if I wanted. There's my 3/2. So, nice, nice. Why don't you try it with log base 6 of, let's try and do an interesting number, 7,776, and see what you get. Make sure that you get a nice even number. I think you should. Is anyone getting that nice even number?
Wait, I asked, like, even number, wait.
I thought so.
No way you can know at the top of your head what it is.
Well, I guess we'll find out if we get an even number. Bingo. Wow. Cool. Give it up for the professor guy. Know some big numbers. All right. This is just an occupational hazard. The nice thing is that it works out pretty even. It used to be that my students would have to do something like this. There's a change of base formula. And if you don't have a TI 80 something, 83, 80, now probably an 84, then you had to do this. Log base b of x, you calculate it as log of x divided by the log of the base. So if I wanted log base 6 of 7,776, then let's see. I'd have to calculate like this. It'd be log of 7,776, close parenthesis, divided by the log of 6, and that should give me the same thing. So it was doable. It's just much more convenient now. It's actually changed the way I teach some of the stuff that we'll see in section 4.5. Okay, are we comfortable with this sheet here? So what I want to do is I want to spend some more time with logarithms and getting you used to logarithms. And for that, we've got another handout that we're going to work our way through. We're going to start with the back side of this. And it says, graph log base 2 by rewriting it as an equivalent expression using exponents. So let's take a look at this expression here. Can anyone rewrite this? In fact, why don't you take a second and see if you can rewrite it for yourself using exponents. And while you do that, I'm going to sketch myself a little t-table. So we're going to have x here and y here. But what would that look like if I rewrote it using exponents? Zach? What to what power equals what?
2 to the second power would be 4, 2 to the third would be 8.
Right? Those are all good numbers. But if I wanted to just rewrite this in general, so let's take a look back at stuff that we did here. When we go from here over to here, when you go from the log to the exponential, really what you're doing is you're starting out with this number, you raise it to this power equals this. So I always kind of think of this as like a tornado symbol on a weather map or something like that. That you got this little circular arrows things going on. So I want to rewrite this one, that to this power equals that. What would that look like? What is my equation here? Anyone? Yeah, thank you. 2 to the y equals x. Now there's something a little bit different about this equation than what we usually get. Usually when we're working with equations, we have y equals something, right? This is not something you can plug directly into your graphing calculator. It won't like it, won't take it. You need to have y by itself. But because we have x by itself, it's easy to plug in values for y and get values for x. So that's turning things around a little bit from what we usually do. Now, if I want to graph this, typically speaking, I want to give myself easy points to graph. I don't want to work too hard. All right, I work hard enough. I don't want to work harder. So let's pick some points that are easy to plug in for, like 0, 1, and 2. Those would be some easy points. And maybe some that are a little bit more challenging, like -1 and -2. But let's start at the bottom and work our way up. So starting at the bottom, if I plug in a 2 for y, what would I get for x? Bless you. 4. Yeah. 2 squared would be 4. How about 2 to the first power? That's just 2. 2 to the 0 power. Anything to the 0 power is going to be 1. Now, do you see a little pattern here? What are you doing to get from one term to the next? You keep on dividing by 2. So what would be this next one? 1/2, and then 1/4. So you're continuing to divide by 2. So, okay, that gives us a bunch of points. And we can see some of those points on our graph. Here, here. Let's see, this one right here. And then some that are a little bit harder to see. But in general, you've got this shape. And this shape is not exactly something new to us. We've seen it before, sort of. We've seen its kind of twin before. But let me talk about where we've seen that for a moment, and then we'll look back at this graph, and I'll point out a few things that you should know about this graph. So let me find, let's see, I think it's here. This is what I want. You've seen this shape before. You've seen it in the form of the exponential functions. Exponential functions are the inverse of your log function. So remember, those inverses are mirror images around each other, or around the line y equals x from each other. So you can see that each of these graphs has kind of a reflection on the opposite side of this line. Now, the graph, the exponential, always passes through 0, 1. What do you think the graph of the logarithm is always going to have to pass through? 1, 0. All those are going to pass through 1, 0. The graph of the exponential grows really quickly. The graph of the log grows really, really slowly. For some of these graphs to get up to, say, y equals 6 or 7, you'd have to go out to the main street to graph that point. It'd just be that far away. These are very slow growing functions. Now, there's a few things that I want you to know about this. Let's see, things to know. Things to know. First of all, that's a slow growing function. It's a very slow growing function. Secondly, it passes through 0, 1. All your graphs of the form log base b of x equals y, they're going to pass through this point. Bless you. Passes through, actually I said 0, 1. I should say 1, 0. 1, 0. And last but not least, this graph never quite touches this line. Just like its cousin on the opposite side of line y equals x, never quite touched the x-axis. Our graph here never is going to touch the y-axis. So the domain of this function is 0 to infinity. And this line, the y-axis, is a vertical asymptote. Y-axis is a vertical asymptote. So let's put that in as well, part of our graph. And I'm going to put it in with a dashed line because it's not really something that's going to show up on your graphing calculator or Desmos when you graph this line, but it is a feature of your graph that I want you to be familiar with. And this is the line x equals 0. This graph never touches it, ever. Comes really close, as close as you want, but it'll never quite touch it. Okay, looking good there. Let's keep it going. We can play around with this graph a little bit, flip it around, translate it, etc. Let's start with, say, this one. Y equals negative ln of x. So what I've got here graphed for us is y equals ln of x. By the way, I think I need to introduce some notation here. ln goes with a particular base. And let me mention two bases here. Log base e and log base 10. Both of these have special notations. The first one is your ln. That's the natural log. The second one is kind of like square roots. When we're dealing with a square root, we don't write the 2 out in front. It's just kind of understood there. If you don't write anything here in the base, it's understood to be the common log. Bless you. So in this example here, on this second side of our handout, we've got the graph of y equals ln of x. And you can see it's not quite the same as the graph of log base 2 of x. It's close. Log base 2 of x passes through y equal 1 at x equal 2. At x equal 2, we're a little bit below 1. So just a little bit different. But overall, the same general shape. Notice you're passing through 0, 1 here. What's the negative going to do to our graph? How's that going to change our graph? Flip it on the y-axis, or flip it on the x-axis. You can flip it around one. What do you think? If you didn't know, what could you do? You can just graph it. So we can type in, for instance, and let me get rid of some of the stuff we don't need to see. And clean that up. So you could graph, say, ln of x, and let me see, put it up here, ln of x, and negative ln of x. Make sure if you're typing in the second of these that you put a negative out in front. Don't use the subtraction key to put in negative log of x. Let's see, where do we want our window? I think from negative 6 to 7 would be good. On the x-axis, negative 6 to 7. On the y-axis, probably negative 4 to 4 would work. It's probably more than we need, really. And there's your graph. So which axis did it flip around? Yeah, the x-axis. So let's see if I can do a reasonable job of graphing this. All right, so something roughly speaking like this. So that's our graph of negative ln of x. Let's keep going. Next one is ln of negative x. How's that one going to flip our graph? Victoria? Yeah, it's going to take this graph and reflect it around the y-axis. So you're going to have a point here, which is going to be the mirror image of this one. You're going to have another point, say, about here, which is the mirror image of that one. So let's see if we can't connect the dots. And that looks pretty good. All right, so 2 down, 2 to go. Let me do this one next. Now there's really a couple ways you can do it. What are you seeing with this graph and how would you do it? What do you got here today? How would you find this graph? We've actually kind of already gotten halfway there in a couple ways. What's overall happening to this graph? There's two things that are happening. What would you describe as both of them? Yeah, it's been flipped around the x and the y. So you can either take this one and flip it around the y-axis, or you can take this one and flip it around the x-axis. Doesn't matter. Either way, it's going to get you the same thing. But these things kind of happen in sequence. So, I mean, for myself, I think I'm just going to take this graph and flip it around the x-axis. So that means this point here is now going to be happening down here. This one's going to stay the same. So something roughly like that. Looking good. Now we've got this one last one to take care of. Personally, I guess I would rewrite this one. I would rewrite it like, let's see. Let's write it like this. Y equals negative ln of x plus 1. Is there a way I can take some of my work, my existing work, and just change it a little bit? Let's see, this was y equals negative ln of negative x. This was y equals ln of minus x. And this is y equals minus ln of x. Is there a way I can get this last graph without having to start all over? Yeah. If you look at this, this is just the yellow graph shifted up by 1. So I'll take this point, that's going to be up here. This point is going to be up here, etc. So you're just shifting the graph up by 1. Thank you so much. And, all right, sorry for the vertigo here. But something more or less like that. That's going to be a graph of minus ln of x plus 1. Let's look at the domain and range of one of these graphs. So let me just pick this one because I got a little bit more room to write over here. Let's think about the domain and the range for our pink graph. Now I'll help out especially with the range, because the range can be kind of confusing here a little bit. But the range, certainly it's going to go up as high as you want. So the range is going to top out at infinity. But eventually, even though it'll take a long time to get there, this will get as low as you want. So the range is going to be negative infinity to infinity. How about the domain, though? How are we going to find the domain? What are we going to think of when we're looking at the domain? Domain is your set of x values. What are those x values? Where does your graph go? Negative infinity to 0. Great. So negative infinity to 0. Does 0 get a brackets or parentheses? Jeff, what do you think? Parentheses, because yeah, it's not going to quite touch 0. Awesome. Thank you, Will and all. All right. So here's kind of the same thing with log base 2. So I'll leave that one for you to look at home. Try and figure out which graphs are which. But let's practice with these, writing them in alternate forms. So for instance, this one's in the logarithmic form. If you were to write it with an exponential form, it's going to look like this. You're going to start out with the base to this power equals this. So it's going to be 9 to the first power equals 9. So a couple of these have logs, a couple of them have exponentials. Let's see what we can do in terms of rewriting them. I'll give you a few seconds to do that. And if you're watching this at home later, you can give yourself a chance to do them as well. Okay, let's take a look at a couple of these. Now some of these you might not know off the top of your head, that's okay. And realistically you've got everything you need already here. So for instance, if I rewrite this one, Nolan, what would that look like if I rewrote it using exponents? Zach, some help?
G to the third power equals 729. I don't get the exact numbers.
It's all right. I think that's a 9. So 9 to the third power equals 729. Looking good there. How about Riley? What's this one going to look like if I rewrite that one? Yeah. 4 to the negative 2 power is 1 over 16. Now, when you're writing them like this, you can always check them on your calculator. If you're looking at that going, I'm not so sure that's right, you can check it just by typing this stuff in. 4 raised to the negative 2 power. Now, this is going to give you a decimal value, but if you just hit the math key, press answer to fraction, bingo. 4 to the negative 2 is 1 over 16th, exactly like Riley said. These are a little bit harder. Dylan, maybe start us off.
Log base 9 equals,
Nice. Log base 9 of 3 is 1/2. And then the one after that's going to be log base 16 of 8 equals 3/4. And the last one, does anyone want to give that last one a shot? Victoria?
Log base 25, 1 over 125 equals -3.
Nice. Log base 125, or base 25 of 1/25 equals -3/2. Now, I'm trying as best I can, and I'd appreciate a similar effort from you, to make the bases a subscript. Don't write them on the same line as everything else. If you were to write, say, for instance, log, let me grab a sheet of scrap paper here. You write log base 16 of, where was our last one? Of 8 equals 3/4. This looks like 168 or 16 times 8. This number needs to be a subscript, so write it a little bit smaller font and below the line where you're writing everything else. If you do that, it'd be greatly appreciated. Sometimes these get a little bit hard to grade, and if you're not careful with that, that actually means something different. Not sure if anyone gets this sense of humor here. What's going on with these two teller windows? Yeah, they're the same. It's just that people always use ln of x. Personally, when I'm teaching, I prefer to use log base e of x because it helps you see more patterns and relationships than ln of x. This is a little bit more abstract, so I do like to use this one a little bit better, or this one a little bit more. In fact, we can rewrite this one using logarithms. So there's a couple ways that I would accept this. If you were to rewrite it using logs, it'd be log base e of 9 equals x. Alternately, you can write it as ln of 9 equals x. They're the same thing. So either one works for this one. And let's see, a little indecision here on my part. Yeah, either one works there. Now these, I think you can do some of these in your head. Let's see if we can do some of them without hitting up our calculator. How about log base, well, let's see, it doesn't have a base here written. Log of 100. Nasser, what do you think? 2. Log of 125, we kind of already did that one, right? We ended up with a 3. And that makes sense. 5 cubed is 125. But let's take a look over here. Why do you think I included this one over here? They're basically the same, right? 5 cubed is 125. Well, what's the answer here, though? 3. Now, the reason I included that one is because there's a property of logarithms that we're going to use that I'm kind of hinting at here. That's a 3 there, that's a 3 there. Oh. So it feels like these things are canceling each other out. In fact, they are. They are because the logarithm is the inverse of the exponential function. So if you do the log of some base and that base to a power, then that should give you a nice quick way to simplify this. What's log base 8 of 8 to the 13th power going to be? We could actually do that one out on our calculators if you're not so sure. There's nothing wrong with that, but I mean the idea is really to do this without your calculators. Let's see, let's go back to the math menu to find our log of any base. That was math and then option A. I think there's another way to get to it off of either the Windows menu or the format menu. I'll check that in a minute. Log base A, and now I've got to do 8 raised to the 13th power. Any guesses before I hit the enter key? 13. And so again, the point here is that these two things are opposite operations of each other, 13 and 13. So that should make your life kind of easy here when you see these things. Now, if these are opposite operations here, these could be opposite operations here. It's just that they're in a different order. Here you've got the exponential function to a logarithmic power, but they're still opposite operations. So somebody do kind of a long shot guess. What would you guess if you didn't have a calculator at all and you wanted to guess something? What number would you suspect here? 26. And again, it's because these numbers match each other. So for instance, these two things are a 4. That's a 26. What's going to end up being here? 26. Now we're getting away from the 26s here, but let me remind you of something that we just learned. ln is really the same thing as log of what base? Log base e. And in this case, I want log base e of 19. So a 19. And that would give me a 19 there. These things cancel each other out. That's kind of nice. All right, why don't you take a second and do the last few on the bottom of this page. Okay, let's run around the room. Olivia, how about the first one? Yeah, nice. Square root of 7 and square root of 7. Great. Those operations cancel each other out. Opposite operations, looking good there. Jeff, how about the next one? E to the log of 1 over pi. Yeah, 1 over pi. Again, these operations cancel each other out. You might understand it a little bit better if you write a e to the log base e of 1 over pi. But that's equivalent notation to ln. So looking good there. And the last one, Riley. Yeah, 15. So that number and that number are going to cancel each other out. So we got a nice 15 here. Logarithms are everywhere in terms of applications. You've probably heard of a lot of them. So where do you see the use of logarithms? Have you ever heard of something called pH? What does pH measure? Yeah, acidity. How much of an acid or a base something is. When you crank up your stereo, the loudness of sound is measured in what? Decibels. And I hope I spelled that right. How about earthquakes? What's the scale for earthquakes? What's that measured in? Does anyone know? The Richter scale. Now, I think that's been replaced by the moment magnitude scale, but the Richter scale is a logarithmic scale. So, wow. Where else can you see it? Well, I'm glad you asked. So, let's see here. 4.3, 4, weight of chain. There's something pretty cool called Benford's Law. I don't think I want to get into that today. I was looking for, yeah, it's called the Tsiolkovsky rocket equation. And basically, if you play around with it, it shows you how hard it is to get into space. And it's interesting that we mentioned space here because we're currently involved in the Artemis space mission. Artemis, in Greek mythology, was the twin of Apollo. The Apollo missions put a man on the moon. What do you think the Artemis mission is going to do? Gonna,
Same thing, a different way.
it's going to put a woman on the moon.
Oh.
So Artemis was the twin sister of Apollo. But the Tsiolkovsky rocket equation is really what you, what's that?
She was also a goddess of the moon.
Goddess of the moon too?
Yeah.
Okay. How cool. That's cool. Thanks for that little tip. But the problem with space travel is that it takes a lot to get to escape the bonds of Earth. 90% of the energy that they used to go to the moon and back and land was used up in getting outside of Earth's gravity. So you use 90 gallons of gas to get outside of Earth's gravity, 10 gallons of gas to travel to the moon, circle it, land, launch, come back, and land again. That was the remaining 10 gallons. So pretty wild. It's just tough. You need a lot of oomph, a lot of fuel to get rid of or to escape the bonds of Earth. You end up traveling like, I think it's like 8 miles a second if you want to get into orbit. All right. Let's see here. So got a couple problems here. These are your first logarithmic equations. One of the things I suggested early at the start of this was that it's really good to have this thing memorized and write it at the top of your test. It's a memory dump. So that way, when you need it, you don't panic, you've got it, and you've got it written down accurately. A place that you might need it is something like this, where you're actually asked to solve for x. Now x, if you look at this carefully, is actually the base of this equation. So, if I wanted to solve for x, one thing I might want to do, or could do, is rewrite it. How would you rewrite it? What would this be as an equivalent expression using exponents?
X cubed equals 8,000.
Yeah, x cubed equals 8,000. Awesome. But I want to solve for x. So how would I solve for x here? Yeah, take the cube root. So x equals the cube root of 8,000. And I think that's going to be 20. Nice. But you're not going to get very far without solving for x, or without rewriting this to help solve for x. Now our next one I don't think works out as quite as nice in terms of the numbers, but it's still workable. You'd rewrite this one as well. Why don't you give that one a shot? Give yourself a moment. Okay, so let's take a look at this one. Riley, how would I rewrite that one? What would it look like?
X squared equals 500.
All right, nice. X squared equals 500. What would x equal? What could x equal? How would you solve for x? Square root. Now here's a little place where I run into a dilemma, because technically it should be plus or minus the square root, but in our case we don't really want the plus or minus, it's just the plus. So let's get rid of that. and just keep the plus. The base of the logarithm has to be positive. So maybe I should add that back here. I think I might already have it. Maybe not. The base has to be greater than 0 and different than 1. So that's a little fact that you need to know about your logarithms. So yeah, the actual base that we'd use here would be just the square root of 500. And let's see. No, I mean you could, I suppose. For instance, 25 would go in there, what, 20 times? Actually, you know what? 100 would go in there. So you could simplify it as a square root of 100 times the square root of 5, or 10 square roots of 5. I'm not really looking for that in this particular problem. I mean, that's great if you do it. Sometimes, depending on exactly how or what you do, sometimes I give a little bonus point there. But let's look at a couple more examples to kind of finish this thing off. This one's example H. This one is in your homeworks. So this is the graph of y equals log base A of x. But we don't know what base it is. So the question is, what's the base? What base would make this graph pass through this point? That's a good question. What would you do? Nice. Plug in x and y. You've got an x and a y, and if we plug in that much, then the only thing that's left unknown is a. So well done, Victoria. So you've got a y is 1/3 equals log base a of 2. Okay. Suggestions from here. Let me rewrite that as log base a of 2 equals 1/3. Maybe puts it in a more comfortable order for us. All I did was just reorder it though. Switch sides on the equations. So what to what power equals what? A to the 1/3 equals 2. All right. So that's a to the 1/3 equals 2. How am I going to solve for a? What am I going to do to get a by itself? Close. You're going to multiply by 3 in the exponent. Keep in mind that something to the 1/3 power is really a cube root. So you could think of it that way or this way. But either way, what are we going to have to do to get rid of this cube root or this 1/3 power? Your thought about the 3 is not that far off. But it's 3 in the exponent. You've got to cube both sides. So we end up with a equals 8. Thanks, Brandon. And last but not least, there's a little bit more on graphs of these functions. In particular, let's take a look at the graph of minus log of 5. What am I going to do to get the graph of minus log of 5? I mean, I've got a couple graphs here. So let's pick this one. That one there. But the graph of minus log of 5. How's that going to change this graph? What's it going to look like instead of what I've got drawn here? Yeah, it's going to flip this across the x-axis. Thank you. So something like that. And let's take a look at some of the things that I might ask for. I might ask for the domain. So let's write down the domain first, and then the range. And finally, the equation of the asymptote, which is really where I want to start. The equation of the asymptote is something I'm going to want you to keep track of, even if it gets shifted left or right. That equation is x equals 0. The domain starts at 0 and goes to infinity. We're not including the 0 because the graph of this function is undefined at 0. If you don't believe me, then do yourself a little experiment. Try taking the log of 0. What's your calculator telling you when you take the log of 0? Yeah, it doesn't like it. In fact, it probably gives you a particular kind of error. It's a domain error. All right, it's just not defined there. That point is not part of your domain. So your calculator can kind of help you out on this one. All right, x equals 0. How about the range? That one's not as clear as this one. Eventually, this graph will get as low as you'd like to go. It certainly goes as high as you want to go. What do we got for the range? Anyone? Yeah, all real numbers. So negative infinity to infinity, or all real numbers. Beautiful. Beautiful. All right. Any other comments or thoughts on 4.3 here? Great. Let's take a break.